Hello and welcome to this talk about synchrotron radiation and how this radiation can be very useful to find solutions to our energy problems. My name is Juan Diego Rodriguez-Blanco and I'm a lecturer in nanomineralogy at Trinity College Dublin. So I'd like to start this talk by giving you some background information about synchrotrons, in case you have never been to one of these facilities. So these are circular particle accelerators and they are very complex facilities. They are very useful because they can produce very intense X-rays, and as you can imagine they are so complex that there are less than 100 in our planet. The way they work is by firing electrons from an electron gun here, and they are moving through a linear accelerator, then injected into a booster synchrotron, and here they increase the energy. And once they have the desired energy, they are injected into this bigger ring, named the storage ring. Here, they move in a circular pathway, and this is being done by using bending magnets, like these sex-to-pole magnets here. And when they are moving, when the electrons are moving in these circular trajectories, they emit X-rays. These are the X-rays that we use to carry out our experiments. Okay. Of course, synchrotrons can produce radiation in other wavelengths, for example, in the ultraviolet or infrared, but most of the research is being done in the X-ray region because this is very useful to understand the nature of matter. These X-rays are brighter than any conventional source, for example, much brighter than the typical single crystal or powder X-ray diffraction systems, okay, and also billions times brighter than the sun. Alright, I'm going to show you here a diagram, animation, showing you how a synchrotron works. So this represents Diamond Light Source, which is in the UK, in Oxfordshire. And what you can see first, this is a building where the control room is located. Here, this is where all the facility is controlled by engineers. And what happens inside the synchrotron is something that you're going to see now. And you will see here the gun producing electrons and how these electrons are fired into this booster ring first. Okay, and when the electrons are fired and they are injected into the booster ring, they are accelerated, they reach the desired energy, and after that they are injected into the bigger storage ring. And here, this is where they produce X-rays. So I'm going to stop the animation just to tell you a couple of things more. Okay, along all this ring, you have different stations to work. They are named beamlines. And each beamline is made of three components. First one is an optic hatch. This is where the X-rays are focused. Second one is an experimental laboratory. This is where you carry out your experiments. And the third one is a control cabin. Okay, this configuration is very important. First thing, the X-rays, they need to be focused. But as you can imagine, this is very intense radiation. So health and safety is very important here. You cannot be in the same laboratory where the X-rays are on, because this radiation is very intense and harmful for our body. So therefore, you always need to control the experiments in this control cabin. You control your experiments remotely. So what happens is that if you want to use a facility like this, what you have to do is to write a proposal. And then, if your proposal is accepted, this is a competitive process, then you can go to this facility for a few days. Okay, one thing that you probably have heard is that there are natural sources of synchrotron light. And one which is very well known is black holes. Okay, black holes can produce synchrotron light because they have magnetic fields, very strong magnetic fields, and matter moving in circular pathways along these magnetic field lines. And what happens is that because of this movement of matter, they produce synchrotron radiation. Okay, the thing is that this is something which is known. This is something that happens in nature. Okay, in different places in our galaxy, and this cannot be confused with the synchrotron light which is produced experimentally. Okay, what I mean with this is that you probably have seen news like this. If it is possible that synchrotrons can produce black holes, and I can tell you an answer in a very simple way. The answer is no. And no, because synchrotron radiation cannot produce black holes. Black holes can produce synchrotron radiation, but not the opposite. Okay, so therefore, all this news and all this kind of science fiction's ideas, no, that a synchrotron could produce black holes and that could be a big problem in our planet, this is not realistic, okay? This is science fiction and not science. All right, so now I'm going to move to the applications of synchrotron techniques. Okay, we use synchrotron techniques to understand matter at the atomic and nanoscale. Okay, it's very interesting to understand the structure and nature of matter that way. And this has applications in all the fields of science. And I'm going just to give you some examples. For example, in life science, it's very interesting to use synchrotron radiation to determine the structures of proteins or macromolecules at the atomic scale. Okay? Also, there are millions of applications in medicine. Okay, for example, from cancer radiation therapy to microbiology, the study of viruses like COVID-19. Okay, also many applications in forensics, because sometimes in forensics there are samples that need to be analyzed and they are very dilute and very small. So synchrotron light has one advantage, and it is that the signal to noise is very high. Okay, that ratio is very high. Therefore, it can be used very successfully in forensics. Okay. Also, for advanced materials, for example, for nanomaterials, nanoparticles, ceramics, light metals, electronics. Okay. Also for environmental science like toxicology, water quality, atmospheric research, or for industry like clean combustion technologies or cleaner industrial production technologies. And as you can imagine, there are a lot of applications in chemistry, from catalysis to analysis of chemicals or the characterization of amorphous and poorly ordered systems. And in agriculture, for example, like plant imaging, genomics, soil studies, and of course, in earth science. And in particular, in earth science, synchrotron radiation is very interesting in mineralogy and crystallography, in research on crystallization and also research in extreme conditions. I mean, high or low temperature pressure, okay? So I'm going to give you some example in earth science, and I'm going to select some examples that can link with many fields of research, which like ocean chemistry or mineral evolution, planetary science or raw material. And this field is crystallization, because crystallization is present in many of these fields. Okay, so in crystallization there is one problem, that we don't understand very well how minerals form and transform. And this happens because these processes are very fast. We know that from a supersaturated solution, we produce crystals. Sometimes this happens by what we call a classical pathway. I mean, you crystallize these crystals by forming nuclei which grow. Okay? Or sometimes it happens by what we call a non-classical pathway. For example, we form pre-nucleation clusters that later form amorphous phases which crystallize. The problem is that these branches, although this looks very simplistic in this diagram here, these are processes which are extremely fast. They can take place in seconds, tens of seconds, and they are very difficult to follow using conventional techniques. So synchrotron radiation, synchrotron-based techniques are very useful for this purpose. So imagine that you are doing an experiment like this in which you are crystallizing a solid from solution, okay, by mixing solutions. So how do you follow the reactions here? You need to take your solids from the solution, and you can do this by using vacuum filtration, and then you have your powder, you put your powder on a holder, you put this holder with the powder in a powder X-ray diffraction instrument, and from here you can obtain structural information. You can identify your phase or phases and to do quantification if needed. Okay? And then you can go, for example, to the scanning electron microscope to do particle size distribution analysis. Okay? So synchrotron facilities can make your life easier because you can obtain much more data. If it happens that your reactions are very quick, you cannot obtain like 1,000 samples. That will be very tedious, very complicated, and in fact, you can run out of sample because your experiment have a limited volume. So how do we work when we need to do synchrotron-based studies? What we do is first we do experiments in the lab, and we make solutions and we use different techniques to characterize the solids, to have a preliminary characterization of the solids. And then we apply for beam time. We apply for beam time at different facilities like a diamond light source, for example, or Argonne National Laboratories. And if our proposal is successful, then we go there for a few days, okay, 3-4 days. All right, there are many different techniques that you can use in synchrotron facilities, from diffraction, scattering, tomography, optics, spectroscopy, microscopy, but obviously when you write your proposal you have to select which one you want to use, because it has to provide the data you want for your experiments. Okay, so we select one. For example, in our case we do a small angle and wide angle X-ray scattering, and what we have to ensure is that we can run our experiments in this facility. Okay, for example, here you have one experiment in which we are mixing solutions, and what happens is that the solution goes through this tube here and through this capillary and goes back. And the X-rays, the synchrotron X-rays, go through the capillary, so we can probe what is happening in our solution with our particles as long as we want. Okay, we can collect data in time intervals of less than 1 second. We can have in situ and real-time data, and that way we can obtain very useful kinetic and mechanistic data. Okay, that's the approach. So overall, what we do is we have our experiments in the synchrotron, and the synchrotron, by using electron, is producing X-rays that will go through our sample. This data will be collected with one or several detectors, and from here we obtain two main pieces of data. First thing is particle size distribution. We can infer what are the particle size distribution as a function of time in our experiment. Second thing is particle identification. What I mean with this is that we can identify which minerals we have in our experiment as a function of time. Okay, and I'm going to show you now 3 examples to demonstrate how useful these techniques can be for us. The 3 examples will go from easy to more complex synchrotron data, and I'm going to focus on critically needed minerals, then on CO2 sequestration, and also on construction materials. So I'm going to start with the critically needed minerals. Okay. Critical needed minerals are these ones which are essentials for the economy. And the problem is that the supply may be disrupted. And typical examples are the elements that are used to build smartphones or computers. Many of the elements that we use to build smartphones are the rare earth elements here in red, or other elements which are gallium, tin, indium, lithium. Okay, these elements are very interesting for modern technologies and carbon clean technologies. For example, the rare earth elements are here on the bottom, the light rare earth elements and the heavy rare earth elements. Okay, these rare earth elements, for example, I'm going to focus on these rare earth elements, they are used for many different types of technologies. To produce magnets, for catalysis, for lasers, for lenses, for batteries, for many more things. They have medical applications, they have industrial applications, a lot. Okay, they are essential every day. And the economy depends on the availability of these rare earth elements for industry. Okay. For example, in Ireland, we use wind turbines to obtain energy, and every year Ireland invests more than 350 million euros in wind energy, because one turbine like this can decrease electricity in 50% and can displace a good number of tons of CO2. Okay, the problem is that these wind turbines, they require half a ton of rare earth elements sometimes, so they are very expensive, and they are expensive mostly because of these rare earth elements. This is a complicated market. Rare earth elements are obtained from rocks, in particular from some deposits which are carbonatite deposits mostly, and the rocks could look like this. If you are lucky, you can have a bigger crystal of this phase named bastnasite, which is a rare earth carbonate. And what happens here is that this bastnasite contains the rare earth elements that we use for industrial applications. But we need to go from something like this to something like that, because we need pure rare earth elements. We need high purity, and each industrial application requires essentially 1 or maximum 2 rare earth elements, not all of them. And the problem is that ideally we would like to have crystals like this that contain, for example, 1 rare earth element. But nature is more complicated like that. So in these crystals, in these bastnasite crystals, what happens is that we find all the rare earth elements in different proportions. So separation is very complicated, and purification is even more. Okay. So also there are not many active deposits that concentrate rare earth elements. This is one in Tanzania. It's a carbonatite deposit. And the problem is that we don't know how the mineral you have seen before forms. Okay, that mineral is named bastnasite, and it is one of the three minerals which are the main sources of rare earth elements for industry. So, as I told you, what we do is to try to mimic what happens in nature by using experiments. So we combine first offline experiments, laboratory experiments, with synchrotron experiments, in this case to understand how a mineral that like bastnasite forms. So we have seen that bastnasite forms from an amorphous phase, and we have synchrotron data showing us that this transformation from amorphous to bastnasite takes place via different polymorphs. They are named lanthanide, tengerite, cosoite, and these ones slowly transform into bastnasite. This transformation depends on the rare earth element involved. The kinetics and the temperature required depend on the rare earth element, and therefore this is a very complex system to work. Okay. So one thing that we have been trying to understand is what happens at the early stages when we form an amorphous phase and then transforms to the first polymorph, lanthanide, because we want to know if something else is forming here. So I'm going to show you one simple experiment using synchrotron-based diffraction, in which you're going to see the transformation from amorphous phase to this mineral named lanthanide, okay? Because we want to know what is happening here. All right. So what we do is we produce this lanthanide here by mixing solutions. Then the solution goes through this tubing and then through this capillary here, and the X-rays, the synchrotron X-rays, are probing the volume of water plus particles in there. So what do we see? That we have here time in minutes, okay, and this is something named 2 theta. If you don't know what is this is coming from X-ray diffraction. So this is an angle, and if you have never done X-ray diffraction, I will tell you 2 clues to understand what we obtain here. If you have no peaks, that means that your material is non-crystalline, okay, it's amorphous. When you have peaks, that means that you have a crystalline material, a mineral, and the position of these peaks will tell you what mineral you have. You can identify your mineral by knowing the specific position of the different peaks. They are named Bragg peaks. Okay, so here what we see is that at the very early stages of the reaction we have an amorphous phase that then transforms into something crystalline, and this is what we have been following by using also conventional techniques. So we have at the beginning an amorphous phase that then starts to crystallize and transforms into a fully developed crystalline material. Okay, so in this case we didn't see anything else forming here. Sometimes in this kind of reaction you can have metastable phases that can be stable for only a few minutes. In this case it didn't happen. So you see here the full transformation of an amorphous phase into lanthanide in a matter of a few minutes. Okay, this is the first stage of crystallization of bastnasite. Okay, we have followed these reactions in situ and in real time at different temperatures and with different rare earth elements. Now, I'm going to give you now more synchrotron data. So I'm going to show you how this picture can be more complex. And I'm going to focus on CO2 sequestration. As you know, there are many projects today to try to tackle the real dramatic situation with increase of CO2 in our atmosphere. So there are many projects ongoing in many different places, but perhaps the most famous one is taking place in Iceland, where carbon is being captured in basaltic rocks in a place close to a power plant. Okay, and here what is being done is to inject water and CO2. They are mixed together, forming something like a soda, and this soda type water is interacting with basaltic rock, and these basaltic rocks are providing elements like magnesium, calcium, iron, and triggering the crystallization of carbonate minerals. Okay, so this is the place. Now it looks like a science fiction landscape, and what you see here is how the CO2 and water is being injected, and what happens here is that when you take samples, cores of the material with time, you see this white precipitate. This is the carbonates. This is carbonates forming via this interaction of basaltic rocks and soda type waters. Okay, water with CO2, with dissolved CO2. All right, we know that this can be done, but we also know that carbon sequestration is also happening in nature. And there are living organisms which are producing calcium carbonate by forming skeletons and cells. For example, you see here one picture where you can see this blue area. This blue area this is not a cloud. This is an accumulation of different algae. They are named coccoliths, and they happen to scatter the light. So you can see this. You could see this from a satellite, and this is light scattered by these coccoliths. These coccoliths are algae, and what happens with these coccoliths is that they are able to produce skeletons, cells of calcium carbonate, of calcite. Okay, they look like that. I'm sure you have seen many of them. So the problem is that here we don't know how this calcite is being produced inside these cells. And why is that? First, because they are very small. You see the sizes here. This is less than 2 micrometers. Second, because there are many organics here and there is life involved. So there is likely high supersaturation processes taking place here which are producing an amorphous phase which is crystallizing later on. So is it possible to mimic these experiments in the laboratory? It is. And this is what we try to do. We try to understand what happens when we have a supersaturated solution similar to what may happen inside these cells, and how crystals can form. Okay, and I'm going to show you some examples of crystallization of calcium and magnesium carbonates. Okay, first, I'm going to try to build this big picture by showing you the many different crystallization pathways that can happen when we only have calcium, carbonate, and of course water. Okay, so here you have a calcium carbonate solution, and this is showing you this solution as a function of supersaturation, low supersaturation, high supersaturation, and there are many different crystallization pathways taking place depending on supersaturation. Sometimes you can directly form calcite from solution, okay? Sometimes you form calcite via an amorphous phase, and sometimes you form calcite via an amorphous phase and some metastable intermediate phases that form quickly by spherulitic growth and transform into calcite via dissolution and recrystallization. Okay, this is a very well-known picture, and what I'm going to show you is what happens following this branch here. Okay, the crystallization from amorphous phase to calcite via vaterite, and also here the crystallization of calcite directly from an amorphous phase. Okay, so this is the perfect example to show you how useful synchrotron radiation can be to follow experiments in situ in real time. Because what you see here is something that took place in less than a minute. So this is 50 seconds, this is less than 2 minutes, okay? So 1 minute of time interval. And this is Suthita. So these peaks are indicating us what mineral phase we have. So at the beginning we have an amorphous phase, amorphous calcium carbonate, and it's quickly crystallizing into vaterite. This crystallization is taking place via one process named spherulitic growth, in which the amorphous phase breaks down and vaterite quickly forms from this amorphous phase, and these are not single crystals. These are aggregates that contain many nanocrystals. Okay, so this is extremely fast crystallization of vaterite, and vaterite then transforms into calcite. The crystallization of calcite takes place much slower compared to vaterite. So you can see that here, this is 20 hours, this happened at 7 degrees C, and what you see here is the peaks of vaterite decreasing and the peaks of calcite increasing. So what you are seeing here is the slow dissolution of vaterite and crystallization of calcite that requires several hours of time. Okay, in this case, at the end, we have single crystals. This is a completely different process. This is dissolution recrystallization. Okay, so this is a different way of showing you the same data. So in order to show you these 3D plots, we can present the data using these graphs in which you have time, and you have here the degree of reaction. Okay, degree of reaction, if you don't know what is that, you only have to assume that this is like 100% of material phases, and this is 0%. This is like the abundance of each phase. So what do we have here? We have amorphous calcium carbonate. These are these white dots, which are breaking down, and quickly vaterite is forming. Okay, and this happened at low temperatures, about 7.5 degrees C, and then after this process what we see is that calcite was growing from vaterite. But here you see the time is different. This is 20 hours, and this was a very long experiment in which vaterite was slowly decaying, dissolving, and calcite was slowly growing. Okay, this is what you see in the pictures. This spherulite of baterite are slowly dissolving and calcite is forming via dissolution and recrystallization. And at the end, you have finally only calcite. Okay? So if you put all this together, you could have a picture like this, in which you have a quick decay of the amorphous calcium carbonate, extremely quick growth of baterite via spherulitic growth, and then a slow decay, dissolution of baterite, and crystallization of calcite. This is the full picture. But it will be impossible to obtain this picture without using synchrotron-based techniques, because you can see here time, and this time is not linear, okay, it's logarithmic, and you see here 1, 2, 4, 8 minutes. So in 10 minutes more or less, half of the reaction has happened. Okay, baterite is fully formed. That will be much more complicated to follow using non-synchrotron-based techniques. All right, and we have done the same, for example, for the crystallization of calcite from amorphous calcium carbonate. This is what you can see here. This is, for example, the decay of amorphous calcium carbonate and the crystallization of calcite, these gray rhombs here, and also the crystallization of magnesium calcite. You see that all the process is gone in less than 1 hour, and we are using low temperatures to decrease the kinetics of the reaction. And here magnesium calcite forms in less than 20 minutes at 21 degrees C. It will be very difficult to follow what is happening if we were not using synchrotron-based techniques. So this is what you see, amorphous calcium carbonate forming calcite or magnesium calcite. Okay. In this case, the process is a little bit slower, but we can use synchrotron-based techniques to follow this reaction with time and see that we have two different crystallization steps in which we form monohydrocalcite, which is a calcium carbonate that contains some magnesium and water, and the first stage of crystallization is quite quick, and then there are two slow growths that occur via oswald ripening. Something similar happens to dolomite. We need high temperatures to produce dolomite, and therefore it will not be possible to follow the crystallization of dolomite without synchrotron-based techniques. You see here at 130 degrees C the breakdown of the amorphous phase, which is a magnesium-rich amorphous calcium carbonate, and the very quick growth of dolomite. This growth is essentially completed in less than half an hour. Okay? It will be impossible or very difficult to take samples from hydrothermal reactors and to study this at high resolution. We need synchrotron-based techniques to study this. What do we obtain at the end? What we have seen is that every time any carbonate forms from an amorphous phase, the first stage of crystallization is usually translated into a spherulitic growth mechanism, because the amorphous phase breaks down very quickly, increases the supersaturation levels in the solutions dramatically, and that is translated into a spherulitic growth of crystalline carbonates. And here you see some examples with calcite, aragonite, dolomite, baterite, monohydrocalcite, and magnesium calcite. Okay, all of them have grown via spherulitic growth because of this quick decay of the amorphous phase at ambient or hydrothermal conditions. Okay, now I'm going to focus on construction materials, my third example. And in particular, I want to talk about one mineral named gypsum. Gypsum is a quite common mineral in nature. It's a calcium sulfate with 2 water molecules, and it can be found in many places. Perhaps the most beautiful one is this one, Nica Caves in Mexico, where you can see single crystals of gypsum, but obviously gypsum can be found in many more places and is used by industry to produce one mineral which is essential, which is named basanite, also known as plaster of Paris. And as you can imagine, there are many applications for plaster of Paris. Every year, billions of tons of gypsum are transformed into plaster of Paris by a simple dehydration. So this gypsum loses 1.5 water molecules when it's heated up at temperatures of 150 degrees C, something that, as you can imagine, consumes a lot of energy and also produces quite a lot of CO2. Okay, so one of the research that was very fruitful a few years ago, it was a very nice collaboration with people from different universities, was to try to understand how plaster of Paris or basanite forms. Okay, so initially we thought that this crystallization pathway of plaster of Paris was going to be similar to to the crystallization pathway in the calcium carbonate system, in which we go from solution to an amorphous phase to vaterite and then calcite via dehydration. So we thought, okay, in the calcium sulfate system, perhaps we will go from solution to an amorphous phase to gypsum and then basanite by losing water. And we were completely wrong. Okay, it happens something completely different. What happens is that these calcium sulfate phases don't grow via an amorphous precursor. They form crystals from the very early stages of reaction. And what happens is that some small nanoparticles made of basanite form from the very early beginning, and they aggregate via oriented attachment, forming bigger rods of basanite. And then this basanite transforms into gypsum. So essentially what happens is that gypsum forms via nanocrystalline intermediates. Okay, we follow this using synchrotron-based techniques. Without synchrotron-based techniques, it will be impossible or very difficult to follow these reactions. And what we found is that yes, we go from solution, then to basanite, then to this gypsum, gaining water. Okay, and the process could be summarized by using a schematic diagram like this, in which you see the nanoparticles, nanorods, coming together via oriented attachments, which is depending on energy, on the surface energy, and then later on transforming into gypsum. Okay, and this is what you can see here, nanoparticles of basanite, and then this oriented attachment of these nanoparticles forming, or these nanorods forming bigger basanite crystals. Okay, and later on transforming into gypsum. So when we follow this by using synchrotron-based techniques, we could follow these reactions using different concentrations of calcium sulfate at different temperatures, also using organics and inorganics, to try to see if it was possible to delay or to slow down the growth of basanite, which is something that happened. But as you can see here in time, things happen in less than a couple of hours. So this crystallization process is very fast, and we can only follow this by using synchrotron-based techniques. Otherwise, it will be very, very complicated. And from here, what we can get is the kinetics of the crystallization, of nucleation, and also the energetics of the reactions. Okay, so this shows how useful synchrotron-based techniques can be to follow crystallization reactions. Otherwise, it will be essentially impossible to obtain so good data. Okay, so what we saw is that yes, we know that gypsum can be transformed into basanite at 150 degrees C, but basanite can form at ambient temperature, and that will be amazing. Okay, because if we could stabilize basanite from ambient temperature, that means that that will be a fantastic way of producing plaster of Paris without having to dehydrate gypsum. The problem here is that this basanite is very unstable. It's not easy to stabilize it for a long time. Okay, so this research was beautiful. It was a fantastic collaboration, and it was translated into very nice papers, including a front cover in the journal Science. All right. So finally, take-home message. So, well, first thing is that the combination, as you have seen, this combination of conventional techniques and in situ and real-time synchrotron-based experiments is fantastic. It's a very powerful tool to study mineral formation processes at the nanoscale. To do experiments in situ and real time allows us to see all the crystallization picture much better. Okay? And of course, understanding these mineral formation processes, as you can see in these three examples I have given you, is key to solve present and future societal challenges. So thank you very much to you all, and also thank you very much to the European Association of Geochemistry for hosting me.